Today, we are going on a road trip to learn about a mathematical method known as hyperoperations, which is a method that mathematicians use to create very large numbers. Before we head off on this journey, we must first analyze some simple mathematical ideas, which will be the building blocks of the hyperoperations that we visit later in this video. The first mathematical idea that we will look at is the successor function. This is a function that simply takes some number n and adds 1 to it. It is this simple function that forms the foundation for a series of operations that rapidly escalate in complexity. For example, if we take our successor function and some number a, then iterate our successor function b times, we find that we have created the operation of addition, where a and b are the two numbers that are being added together. If we take this one step further, we see that if we iterate the addition of a, b times, we create the multiplication operation, where a and b are the two numbers that we are multiplying. Now that we've covered these ideas, we can begin our road trip. Our first stop will be at the well-known exponentiation operation. Similar to the operations that we just looked at, exponentiation can be described as the iteration of the multiplication of a, b times, where a becomes the base of the exponential expression and b becomes the exponent. This is the beginning of our hyperoperation sequence. In order to express what level we are at in the sequence, we are going to swap out our conventional notation with numbers in brackets to signify the level we are at in the sequence. It must be noted that this new notation simply changes the appearance of each operation, not its function. So a 1 in brackets adds two numbers, a 2 in brackets multiplies two numbers, and a 3 in brackets exponentiates. Let's hit the road again and head to our next hyperoperation in the sequence. The next hyperoperation is known as tetration. Tetration can be described as the iteration of exponentiation. But what does this look like? How do we iterate exponents? In order to understand how we do this, we must remember that in our new notation, exponentiation can be written as a, open brackets, 3, close brackets, b. Using this notation, the iteration of exponentiation b times looks like this. This is tetration, and it is typically notated like this, where the 4 indicates that we are at the fourth hyperoperation in the hyperoperation sequence. To understand this better, let's look at an example of tetration. In this example, our a value, which represents the number that is being operated on, is equal to 3, and our b value, which indicates the number of iterations of the previous hyperoperation, is also equal to 3. So, writing this out, we would get this expression. In this expression, we have 3 3's, and the number inside the brackets is 3. So this indicates that we have iterated the exponentiation operation 3 times. We can now simplify this expression, as we know 3 exponentiated to 3 is 3 to the power of 3. And we know that 3 exponentiated to 3 to the power 3 is 3 to the power 3 to the power 3. From this, we can see that tetration will always result in a power tower of BA's. So in this case, we have created a power tower of 3 3's, as our value of A and B was 3. This will be important to remember for when we reach higher level hyperoperations. We are only at the fourth hyperoperation in the hyperoperation sequence, and we have already created a number of magnitude 7,625,597,484,987. That's massive. So tetration can create some very large numbers, but our next hyperoperation blows tetration out of the water. The next hyperoperation is known as pentation, and it gives mathematicians the ability to construct astronomically large numbers. As you may have guessed, pentation is the iteration of tetration, and thus it can be written like this. It is notated using a 5 inside the brackets, as it is the fifth hyperoperation in the hyperoperation sequence. Let's look at an example of pentation. Once again, we will use 3 as our value for a and b, so our expression is 3 pentated to 3. This is equivalent to this expression, where the 3 threes and the 4 inside the brackets indicate that we have tetrated 3 times. We have seen the expression inside the parentheses before, so we can quickly clean this part of the expression up by repeating what we did earlier. Now we have the tetration of 3 to the power of 3 to the power of 3, and as shown earlier, when we are tetrating, we can write the expression as a power tower of BAs. So this expression is equal to a power tower of 3's with 3 to the power of 3 to the power of 3 3's in it. We calculated earlier that 3 to the power of 3 to the power of 3 is over 7.6 trillion. So this number has over 7.6 trillion 3's in its power tower of 3's. It is truly astronomical. But we aren't done yet. We are leveling up one more time to a hyperoperation that gives us the ability to create numbers that are unfathomably, astronomically, inconceivably massive. The last hyperoperation that we will look at is known as hexation. It can be defined as the iteration of pentation, and as a result, we can express hexation like this. We notate hexation as A, open brackets, 6, close brackets, B. Let's once again substitute 3 as our value for both A and B in this expression. Now take a breath, because you're about to witness the creation of an absolutely massive number. Are you ready? Let's do it. We know that 3 hexated to 3 can be rewritten as the iteration of the pentation of 3 times, which can be conveyed as 3 3's with a 5 in brackets between each 3. We can simplify the expression in the parentheses, as we know that 3 pentated to 3 is equal to the iteration of the tetration of 3 times. This can be conveyed as 3 3's with a 4 in the brackets between each 3. Next, we know that 3 tetrated to 3 is the same as a power tower of 3 3's, or 3 to the power of 3 to the power of 3. Following this, we have 3 tetrated to a power tower of 3 3's, which is equivalent to a power tower of 3's with 3 to the power of 3 to the power of 3 3's in it. This number in the parentheses will then become the number of iterations of the tetration of 3. Are you still with me? Here comes the mind-blowing part. Let's take the last tetration in our expression and find its value. We know that this expression is equivalent to a power tower of 3's with 3 3's in it. Now let's get the second to last tetration and find its value. We know this expression is equivalent to a power tower of 3's where the number of 3's in the power tower is equivalent to 3 to the power of 3 to the power of 3. If we now get the third to last tetration and find its value, we find that there is a pattern occurring here, in which the previous value that we calculated becomes the new number of 3's in our current power tower. And it is this pattern that continues until we have tetrated this many times, as this number was the number we calculated to be the number of iterations of tetration that we had to complete. This number is incomprehensibly massive. We only scratched the surface of hyperoperations in this video, as the sequence is infinite, meaning that the levels keep going up and up, reaching numbers like Graham's number, tree theory, Rayo's number, and higher. If you'd like to see an application of hyperoperations, you can watch my tree 3 video, where I use hyperoperations to describe Graham's number. In that video, I use a notation known as Knuth's up arrow notation, which is not very different from the notation we learnt here today. And that was the hyperoperations road trip. I hope you had some fun, and I hope you learnt a little something about the amazing capabilities of hyperoperations.